Right, I just want to finish a little topic on statistics just by talking about the subject in general, because a knowledge of statistics at GCSE level and would help you to understand the figures that you're being fed through the mass media and so on more readily, and it's worth building on the knowledge in order that basically you're not sort of deceived so often as you probably are. I've already recommended the BBC Radio 4 programme, More or Less, which is not actually on every week, but it's worth listening to. Just talk about... I've mentioned some of these topics briefly already. I've mentioned things like random numbers, the way that random numbers work. I've talked about things like traffic black spots, which can just occur from nowhere because that's the way random numbers work, and likewise they can go away just as easily if no one does anything about them. There was at one time a few years back concerns about leukemia being caused by electric pylons, and that appears to be a similar thing, that you have clusters of children and so on seemingly being affected, which could be put down to living close to electric pylons, but it's like the traffic black spots. It's just isolated incidents. A greater analysis of on a national basis or a more widespread basis just shows that there is no connection between living by an electric pylon and suffering an illness or whatever. I don't know whether the same sort of logic applies to people nowadays who claim that living next to a mobile telephone radio mast will cause them to contract all kinds of illnesses and so on. It's just the same sort of rubbish, really. There's no actual mathematical basis for claims like this. And also, one example that I've come across quite a couple of times, well, not too often, but a couple of times, is the claim that a full moon will cause people to suffer more medical problems and all this type of thing. And I remember very clearly that a professional nurse told me this, that they have to work more harder and they see more cases when there's a full moon. But again, there's just no mathematical basis for this. I don't know where. I'd probably like to meet the same nurse again to discuss things further, whether it was confirmation bias or just not generally taking any too much notice of the statistics and so on. Who knows? But this. Because I'm interested in astronomy, a lot of these examples that I can come up with in general do stem from statistics. These are a list of the supernova that have been seen in our galaxy in the last 2,000 years. Now the statistics tell you that we can see a supernova once every 400 years on average. But having said that we can see it once every 4 years on average, these supernovae are not occurring on a regular basis of every 400 years. But that does not attack the hypothesis that supernovas occur on average every 400 years. As you can see, with the sort of type of equipment we've got now, it would be very handy to have a supernova now. It's been over 400 years since the last one. It'd be quite handy to have another one now with all our available astronomical equipment we've got nowadays. But the fact that it's been over 400 years does not increase the probability of there actually being a visible supernova compared with, say, the year 1700 or whatever. Okay, so what I'm stressing is the statistics say that on average a supernova will be visible once every 400 years on average, and that's what it looks like in real life. Stretching the problem a bit further, I could say that most of our galaxy is hidden by dust. So the actual supernova rate is something like 1 in 30 years actually, and the last nearby supernova is 1987 in the Magellanic Clouds, and we were able to detect that by neutrino emissions and so on, emissions that would allow us to detect any supernova within our own galaxy. So we know that there has not been a supernova within our own galaxy since 1987. Again, on average we expect one every 30 years, but again, the fact that the probability of one occurring tomorrow is not any higher than it would have been in 1990 or anything like that, you know. So that's the way random numbers work. Now, I was going to talk about one case you always quite commonly come across is a case of Sally Clark. Now, Sally Clark was sent to prison in 1999 for murdering her 2 infant children, and the way it's reported is that there was a major problem with the mathematics behind this. I mean, it's a big subject really. If anyone has anything to add to what I'm about to say here, I'll be welcome to hear about it in the comments, because obviously well, basically not just the original court case, but the whole thing went on for years. So there's all kinds of ins and outs here, which if you feel you've got anything to contribute, I would be glad to hear about it. But essentially, I think I can mention names here. There was a retired professor called Meadows who gave went before the court and said that the chances of these 2 babies dying purely by natural causes was that 1 in 72 million and so on. And the way he achieved this was to say that the chances of 1 baby dying from natural causes would be this 1 in 8,500, and so the probability. I'm sorry for the gruesome subjects here, but this is quite often the case in probability. So the probability of the first baby dying and the second baby dying, he said that it's that multiplied by that, which would give you 1 over that figure, 72, whatever. Okay, so that's how he arrived at his figure. And he went through in front of the court explaining this, and he pressed it even further. He said that this is equal to winning an 80-1 bet on the Grand National 4 years in a row, and things like this. So he really tried to press this figure home. And well, ultimately this is wrong. I should say before that I mean this figure was repeated by the press and so on. It was backed fully by the professor, as I said, in several ways. It was repeated by the press and so on, and it went through that Sally Clark was found guilty and sent to prison, despite the fact that more responsible mathematicians, if I can call them that, were criticising it heavily. And well, maybe you might be able to guess why we would want to criticise this. I mean, as it's stated here, a GCSE student might be able to should be able to work out the problem with this. And the problem is that this is a formula that only works if the 2 events are independent. And if you have babies dying, then obviously there's a good chance that they won't be independent. If there's something genetic, then it's not too surprising. If you know what I'm saying. I'm sorry for the way I've stated that, but it's not too surprising if 2 babies do die if there's a genetic problem, or you can think of all kinds of other things that whereby the death of the first baby could influence the probability that the second baby would die and so on. There's a major problem with this, and well, that's it in a nutshell. I mean, essentially, she was eventually let off. Well, when I say let off, she was released from prison in January 2003. So she'd spent a fair time in prison, and she was only actually released on her second appeal. The first appeal went through. As I say, you had mathematicians who were obviously by then highly worried about this. But despite that, the first appeal went through, and she lost that. So it had to go through to a second appeal before she was released. And even then, the thing didn't stop. I mean, there's another woman was. This was January 2003 that Sally Clark was let free. In June 2003, another woman was put on trial, but eventually found not guilty. But they allowed the Professor Meadows to act as a witness in that case, despite the previous events with Sally Clark. Although, as a result of that, Harriet Harman from the British government did put a block on him being able to appear in court in future. And in December of the same year, 2003, another woman, Angela Cummings, who had been sentenced to prison for the same reasons or similar reasons, she was let free as well. But again, that was only on a second appeal. And there's enormous, when I say enormous, there's a lot of what are called zombie statistics here, or zombie information, because even then the issue was not put to rest. In 2005, the editor of The Lancet, which is a British medical magazine for doctors, did actually write an article in support of Professor Meadows, despite everything. And Professor Meadows was actually struck off the General Medical Council at a later date, but he appealed through the court. It went through courts, High Court and everything, and he was eventually eventually allowed back. His registration was eventually allowed, so that he was actually allowed to practice it as a doctor. Although obviously his reputation as a professional witness in court had obviously fell by the wayside by then. And it's just an enormous issue, it's just quite incredible. So, as I said before, if you've got anything you can feel you can add to this, then please feel free, because it is quite a major topic, quite interesting from a mathematical point of view, and the way that, basically I suppose the way that a lot of people don't accept the mathematics, it's, yeah. Now another topic would be the lottery. The lottery in Britain, anyway, you have to pick six numbers from 59. And the actual probability of winning is 45,057,473. So basically you've got a very, very small probability. I mean, you shouldn't really have to say this really, but basically you've got no real chance of winning the lottery, so you're best saving your money. I mean, I tend to say this in the evening classes and so on, that hopefully one result of studying mathematics will be that if you did enter the lottery beforehand, then you could perhaps take the hint and don't enter in the future, and any saved money would offset any fees that you've had to pay for this mathematics class and so on. Yeah, you've got no chance of winning, essentially. I mean, obviously you can win smaller prizes for getting a smaller number of numbers correct, but even then the chances of winning are about 10%, and it's a bit like a one-man bandit in a pub. If you keep on doing it, then you're eventually just going to lose it all, even if the chances of winning are 10%. So my recommendation would be don't do it. If you apply a bit of mathematics here to it, well, again, from your understanding of the situation, hopefully you can see that this is an independent situation, the drawing the balls. Okay, the balls are just drawn at random. The balls don't care about what numbers have been drawn in the lottery the week beforehand or the week before that. It's purely independent. You draw one number and then you throw it away. Then you pick another number. The probability of picking the other number is not affected by the first ball you've drawn out, and likewise the probability of the third ball is not affected by either of the two balls that you've drawn out beforehand. So it's an independent situation. So you could say, okay, the chances of the first ball being drawn, or the chances of one of my numbers being drawn as the first ball, is 1/59. Now, probability of the second one would be 1/58 because there's only 58 numbers left. And you go like that, go down to 1/54. Okay, so it's my first number and my second number and my third number. so I can multiply it because it's an independent situation. You know, as I said before, there's no chances of the second ball drawn. The probabilities of the second ball being drawn. There's no chance that its probability of being drawn is affected by by what number was drawn first, and so on and so on. And you could do this and get an enormous number, which is actually more larger than that. But at least you got an idea that it's an enormous number. Now, actually, to explain what's happening here, I could probably just state that because of the independent nature of this, because of the independent nature of the way these numbers are drawn, that combination, or I should say that permutation, has got exactly the same probability of being drawn as any 6 numbers that you've put down. Okay, you might think you've put down those numbers at random, but the probability that your 6 numbers will be drawn will be exactly the same as the probability that this number will be drawn. So going back to what you've got here, you've done that seemingly correct, and you've got a number which is larger than that. But the reason for the difference is essentially that you've probably just considered, for example, you've just considered that permutation, whereas if it was the other way around, if you'd had 6, 5, 4, 3, 2, 1, then you would also have won. So you need to take into account of all these different permutations. So that reduces your chances of winning from this enormous figure you've got here, and it goes down to this, but it's still enormously large. So, as I said, best not to throw your money away, in my humble opinion. But having said that, one thing that is you can deduce from this is that just because the probability of something happening is very, very small, that does not mean that it's not going to happen. Okay, the probability of you winning the lottery is enormously, exceedingly small, but nevertheless, every week someone does seem to win it. It does seem to happen. Perhaps how long have I been going now? I'm going 11. I could probably just give a quick mention of what's called the Monty Don, I think. I mean, what I'm about to say now might seem obvious to various people, but in practice, you know, it's not everyone will actually realise this situation. So I'll probably worthwhile talking it through within the concept of GCSE mathematics. I've just realised actually that I've forgotten something. When I was talking about the lottery, I was going to show you this from The Sun, a British publication. And this says, here are the numbers most likely to be drawn. Picking them could up your chances. Well, I don't need to spend too much time on this. From what I've just said, this is just nonsense, okay? Right. Now, on the Monty Don scenario, what you got is you're in a quiz game and you've got three doors, and you know that the star prize is behind one of them, and you have to pick at random which one you're going to choose. So, I mean, you've got no information whatsoever, so you pick one, the chances of each of them is a third. So you pick one, and the chances of you winning is a third. Now what they do is then you choose one, and then they take away one of the doors, i.e. one of the doors which did not have a prize behind it. So you now know that the prize is behind one of these doors. Now if you'd chosen that originally, then what's going to happen is that although they've got 2 doors left, your chances of winning are still exactly 1/3. Nothing has changed. So therefore the probability of being behind the other door is 2/3. You know, the probabilities must add to 1. That's the case. Or they replace that one single door from these two separate doors, so that must be 2/3. Whichever way you look at it, that must be 2/3. And the one you've chosen this one here, which is the same as this one here. Your probability stays at 1/3. Okay, it's like on Who Wants to Be a Millionaire. If you have not got a clue about any of the answers, or even the question I should say, where you've got to just choose an answer totally at random, then your chances of winning is going to be a quarter. If they then take 2 of the answers away, so you've just got 2 answers on the screen, that makes no differences. That makes no difference. Your chances of winning are still going to be a quarter. Because nothing's changed, So going back to this scenario again, that's what you got here. Your chances of winning are still going to be a third, and you've got 2/3 chance that it's behind the other door. So what do you do? Well, what the statistics is telling you is that if you, I should say, they now give you a chance to change doors. So what should you do? The statistics is telling you that if you choose doors, your chances of winning are double what it is if you stay where you are. Now, the reason I'm really saying this is it's just a very useful idea for explaining what statistics is telling you. It's telling you that it's suggesting that if you swap doors, your chances of winning will double. It's not telling you to do anything in absolute terms. It's just suggesting, double your chances of winning by moving there. It's not telling you that you're going to win. You're not going to win. You're not definitely going to win by doing that. It's just your chances are going to double. So you've still got a bit of a perplexing choice to make. I could put what I've done now. I could just probably finish on a couple of things that come to my mind just in the last few days, really, not for any other reason than that. I've got this one here, says that I live in Wales, approximately 1 mile from my town centre, and I can guarantee that it will now take at least twice as long to drive there, about 5 minutes rather than 1 minute that Mark Dreyford estimates. Well, Mark Dreyford did not estimate 1 minute. He said that it was an average. And that's the thing with averages. Some will be greater than the average and some will be less. Averages just do not apply to anyone at all, really. When they talk about averages, things like the average cost of living going up and all that type of thing. The average cost of living is a cost that does not apply to anyone at all, really. People will either be greater than the average or less than the average, but the average will not actually apply to anyone. This one here is saying, Mick Jagger is 80, Mitch McConnell is 81. The benefits of a life of sex, drugs and rock and roll should not be ignored. Right, so I mean, this is obviously posted as a joke, but there is some mathematics to be taken from this, and that is that small samples don't count. Particularly when you've got a small sample as you can get, just 1 per. Okay, that doesn't actually show you anything at all of any real meaning. This is something from a recent by-election. Only Labour can beat the Tories. Well, you can see from the figures here, they got 29% for Labour and 29% for the Tories and 22% for the Liberals. Now, that's 29, that's 22. That's just not the way that you represent bar charts properly. And this is, someone's made a comment on this, but the actual real initial article was here. Prices must drop now, inflation has fallen. Well, that's just not true. If inflation is going up, then prices will go up as well. As long as there's inflation, prices cannot go down. Right. Anyway, thanks for staying with me. See you again.